We are live. It is, it's November 19th. Is it November 19th? We are live. It's November 19th. It is a Tuesday, and we are recording our first lesson together. Normally people don't clap for that. Today, we're going to learn a new derivative rule called the chain rule. And what this applies to, and this is going to bring back some of your knowledge on composition of functions, so an inside function, an outside function, and we're going to talk about a rule for what happens when you have the derivative of a composition of functions. So let's get started. We'll talk about outside, inside. We'll talk about repeated use of the chain rule. That actually might be tomorrow. Chain rule is you're going to have to believe me now. Chain rule is probably the most widely used differential rule. Chain rule is all over the place. It's going to be useful with exponential functions, with trig functions. At this point, we've really only been able to do the derivatives of really simple functions, but we're now going to be able to do derivatives of things that are really cool and complicated. Things to keep in mind. The ddx symbol is like an operator. It means you're about to do something to a function. You're going to take a derivative. It's an active process, this whole idea of taking the derivative. And to kind of introduce the idea, take a look at this function x squared minus 3x plus 4 all to the 60th power. This is certainly a more complicated function than what we have dealt with at this point. And there's something special about it taking its derivative. And what rule would you like to use on this? You'd like to use power rule. It sure would be nice if we could just use power rule and make the 60 and put the 60 in front and make it a 59, right? Wouldn't that be really great? Be great. But there is something that's a little bit more complicated than that. So what I'd like you to do to begin with, I'm going to go to this really quickly. I'm only going to have you take about 2 minutes on this. But what I'd like you to do is find a partner. We make eye contact, no verbal communication with a partner yet. Eye contact. Whoever is older, I would like you to work on these functions. And I would like you to do basic power rule. I would really like, and here I'll do the first one for you, and you're going to do the other ones, and they'll be really fast. But when for the first one, I'd like you to just do y prime is equal to 2 times the quantity x plus 3 to the first power. Pretty simple power rule problem, right? So whoever's older, I'd like to do power rule on all 4 of those. It's going to be really quick. Whoever is younger, I would like you to write it out as a product, and I would like you to use product rule to do the derivative. Now, whoever's older, once you're finished, you can help with product rule. But I'd like to take about 2 minutes to do this, and find your partner and all right, so hopefully this kind of matches up with what you did. I don't want to do a ton of explaining on this, but hopefully this matches up in some ways. If you were the older person, your work should look something like this on the left. Okay? Very simple idea. I'm going to tell you, we'll go ahead and dispel any myths right now. If you were the older person in the pair, you did it wrong every time, but you did it the way you were told. Okay? Now, partner B used product rule, if they did it correctly, used product rule, and product rule is a rule we're comfortable with already. It's in our happy little place. We've used product rule. We're happy with it. And would have gotten something like this. The key here now is look at the 2 results and draw a conclusion about the differences. What's the same and what's different? So what's the same? They both have a 2. They both have a 2. They both have a 2x plus 3, but the one that did power rule had something extra. Okay, we'll talk about that as we move on. Is that okay? Is that consistent with what you did? Let's go to problem 2. Partner A did it wrong, but if you took a simple power rule idea, you put the coefficient in front, you reduce the exponent by 1. That's not the right answer. It's a nice simple process though, right? Partner 2 did something similar. They ended up with something similar. We'll notice again what's the same and what's different. The 2x is new. And the question for today is, where did that 2x come from? Why is it right? And how does it apply to what we're about to do? Okay, good so far? Let's go to 3. If you got this far, this is what the older person would have gotten. On this side, again, not the right answer. Simple power rule idea. Coefficient or exponent becomes coefficient, reduce the exponent by 1. The point here, if you haven't caught it already, is there's something missing from what the older person in each pair did. What's missing? This thing is extra. Everything else is the same. Good so far? Many of you have wheels spinning. You're thinking right now. This one makes it even a little bit more clear. Partner A, the older person in the pair, did it wrong. But I told you to do it that way, so I'm not mad at you. Partner B, if you had used product rule, and we know product rule works, right? Could prove it if you want. We didn't really spend any time on formal proof, but you believed it. What's here that's not here? Negative sine x is over here. And what is negative sine x relative to the original equation? It's the derivative. What's 6x squared plus 3 relative to the original equation? It's the derivative of the inside. What is 2x relative to the original equation? It's the derivative of the inside. You know what the next answer is going to be, guys? What's 2 relative to the original equation? It's the derivative of the inside. So what we're about to learn, here is the actual formal notation of it, one of the formal notation for it. This is called chain rule. So go to the back of your notes and write chain rule on top of that. The alternate notation for chain rule, there's two ways we can look at this. One of them is traditional function composition notation. The derivative of a composition f of g is the derivative of f of g with respect to, there's an s in respect, with respect to g of x times the derivative of g with respect to x. Question? It must be recording the whole screen. Oh well, I'm recording the windows moving around. I'm recording more than I want to record, but life goes on. It all happened when I paused it earlier. Okay. I'm still recording, but it's not recording the red window like it did when we started. We'll be okay. All right. So here's the idea. If we can identify an inside function and an outside function to a composition, we can follow a predictable rule. I realize the notation isn't real pretty right now, but it's going to make sense as we move on. Okay, so believe me that it's going to get better as we go on. But we've got to differentiate an outside function. We've got to differentiate an inside function. We've got to put the pieces together. Okay, I want to go to that function we just did to demonstrate one of the applications of the chain rule. I don't want to do the one we just did. I want to do the 60th power one on the front of your notes. What was that function? X squared. There was a 3x. There was a 4, and there was a 60th power. Okay. I want this derivative. Okay. There's two ways to do this. I'm going to use the dy and the du notation first, and then I'm going to use the composition notation second. So the first thing, what I'm going to do is I'm going to let u of x be the inside function. Okay? So in this example, I would say that u is equal to what? X squared minus 3x plus 4. Okay? I'm going to let the outside function be a function of u. Okay? So if u is the inside, what happens to u in the original? I'm not doing a derivative yet, but the outside function could be written as u to the 60th power. Okay? Now I'm using this definition. The derivative of y with respect to x when I have an inside function u is dy du times du dx. So we use calligraphy then makes u's look weird, but right? So we want du dx and we want dy du. Okay? The outside function is y and the inside function is u. So what is du dx? That's the derivative of u with respect to x. This is an easy one. I hear whispers of it. 2x minus 3. Good? Okay. What is dy du? Now, du is weird. We haven't seen du yet. We've seen dx's most of the time. If if y is u to the 60th, what is dy du? What is the derivative of u to the 60th with respect to u? Just pretend they're x's, right? Except use u's. What is it? 60 times u to the 59. Good so far? We haven't done anything earth-shattering yet, have we? Okay. Now I'm going to take these two things, and I'm going to put them where they belong. That goes there. That goes there. So dy dx, the derivative of this thing that I'm trying to find the derivative of this thing, is dy du times du dx. Are you happy with that notation, and should we call it done? What's wrong with it? There's nothing wrong with it? What's wrong with it? It's got a u in it. We just introduced this function called u, and our u is in our answer. Do we want u in our answer when we're looking for a derivative? No, we want a derivative with respect to x, so we're allowed to have x's in it. Do I know what u is? Huh. Your English teachers would be mad right now. You know what u is? Do we know what u is? Is u okay? What is it? What's u? U is this function, right? So I can put in place of this 60, 59th power, I can put this x squared minus 3x plus 4 thing. And I have 2x minus 3. Now, which kind of leads us to the, I'm going to show you the process by writing it out and identifying outsides and insides. But I really want you to know that this process is, if you know how to do the derivative of the outside function, you do it. But you leave the inside the same. And then you multiply by the derivative of the inside. So there's a little bit of a shortcut to this, but I want to show you a couple more examples, kind of identifying the outsides and the insides first. How are we doing? What's up? That is the final answer. I'm not going to spend a lot of time. You'll notice with chain rule, we're not going to spend a ton of time simplifying answers, especially when the functions get weird. Okay? All right, so let's go to this next example. And I'm going to use a slightly different notation because I think it's a little bit cleaner for this one. And we're going to be able to use both. And AP wants you to be able to use both notations and be familiar with them because they might throw them at you in a couple of different contexts. We'll keep practicing as we go. I want the derivative with respect to x of a fraction to the 6th power. Yuck. So let's first identify the inside function. I'm going to say that, in general, a composition is going to be written as f of g. Now, for many of our practices, I will have g as the inside, f as the outside. You need to allow yourself to be able to switch them, because it's not always that order. But for today, I'm going to identify the inside function as g of x, and g of x is which one? What's the inside function in this thing? It's the fraction thing, right? G of x is the fraction thing. Okay? And I'm going to identify the outside, but I'm not going to use x as the variable. I'm going to identify the outside function with g as the inside. So the outside function I'm going to call f of g. F of g is what? g to the 6th. Keeping in mind that g is a function, right? G is kind of a nasty function. Okay. Now we need both those derivatives. Which one's easier? Derivative of the outside or the derivative of the inside? Let's do the easy one first. The outside's easier. What is the derivative of the outside? What is f prime of g? 6g to the 5th. Great. Now, what rule do we need to use for the inside? Good, quotient rule. G prime of x is equal to, yuck. I'm going to kind of cruise through this. Will you do it on your own, and we'll make sure we match here at the end? And I'll kind of talk out loud as I do it. I got low, D high, less high, D low, down below, low squared must go. And I'm going to do some simplifying. Try to do some simplifying with the numerator in a quotient rule problem. So it'll be 6x squared plus 4 minus 12x squared minus 6. Thank you. 6x. Great. Thank you. That helps me a lot. Negative 6x squared minus 6x plus 4 all over 3x squared plus 2 quantity squared. And something you'll notice, and we've talked about this before, but when you're doing quotient rule problems, you're never really going to FOIL the denominator. You're going to leave it as a squared. Okay? Once we have those derivatives, we're going to put it all together. H prime of x is f prime of g times g prime of x. F prime of g is 6g to the 5th. G prime of x, big nasty fraction, negative 6x squared minus 6x plus 4, all over 3x squared plus 2, all to the 2nd power. You don't want to leave your final answer with anything other than x's in it, right? So let's substitute back in. Now, some of you are going to skip this step, and I'm okay with it. But I want you to be able to put the g back in. So however you get there is okay, but this needs to be written as 6. And we need that original, I need that original function back. 2x plus 1 over 3x squared plus 2, and then I multiply by the derivative of the inside. Raise your hand if you want to do some simplifying now. One hand went up just by default. It's okay. Do you want to simplify? Not really. And we're not going to spend a lot of time doing it. But we have applied chain rule correctly. I think I like to look at the frame of it. 6 something to the 5th is the derivative of the outside. The inside stays the same. And then you multiply that by the derivative of the inside. Questions so far? Okay. As a side note, guys, we've already done stuff like this. What's the derivative of e to the 6x? Does that make more sense now than it did before? Do you see where the 6 comes from? 6 is the derivative of the inside function. So we could do this from a, so this would be f of x, or let's say f of g would be e to the x. The inside g of x would be 6x. Well, g prime is 6. F prime is e to the x. Or e to the g, I should say. F of g is e to the g. Let's do it that way. Put that into a little bit better perspective than it was before. It's one of those things where I told you a week or two ago that you just kind of had to believe it, but now chain rule is the reason it is what it is. Okay? I would like you to go to this one. Example 3, we'll do the triple chain rule another day. I'm not going to throw a triple chain rule at you today. We've got a composition of a composition of a composition in example 2. Let's save it for tomorrow. But what I'd like you to do is write out notation here. We're asked to find a couple of h primes. I'd like you to say that h prime of x is equal to f prime of g of x times g prime of x. And I'd like you to take just a couple of minutes and see if you can get h prime of 1 and h prime of 2. Just to finish this up then, guys, we'll talk more about process tomorrow, but I hope you got 21 and 20. What I would like you to do is check that. If you didn't get that, let's have a quick conversation. I'd like you to do 3.7 day 1 homework. Show some work. I really think that some of these, at least for the first handful of that you try, you really need to show some work. Because as soon as these things get complicated, you're not going to be able to do it all in your head. So try as much as you can of 3.7 day 1. We'll do 3.7 day 2 tomorrow. We are looking at a quick quiz on Thursday in the formative category, 3.8, and then we'll do a partner quiz again next week. So we'll go from there.